Welcome. Today in this lecture, we shall be covering a few more illustrations on the microscopic balances. So, first problem we shall be considering will be flow between tapered plates. Now, you see that in many applications, industrially or in our research, we find that many times the flow does not always happen over a conduit or over a free or unconfined surfaces. Sometimes these flows are also confined within some plates. Like for example, we may have a flow through two concentric circular plates through which some flow is going, and this kind of flow configuration in a similar fashion you find that is used for constructing some heat exchangers or some mass exchangers, and there we get some kind of change in the heat transfer and mass transfer characteristics. Also, you find that this kind of flow between two channels are also found in some viscometers, where we are having some kind of fluid and we are trying to rotate one particular plate over another, and during that we measure the stress that is obtained, and we find from some formula we obtain the viscosity. So, in that we will find that there are many applications where the flow happens through two plates, and these plates may be parallel or they may not be parallel. So, they may be sometimes tapered. If you look through the flow through some kind of nozzle or this diffuser, for example, if these nozzles or diffuser are used in the space shuttles to get the thrust to lift the particular space shuttle. Also, you find that to find the velocity or flow rate, you use the venturi meters, which is also kind of converging diverging sections. In that case also you find that you have the particular flow going through this kind of tapered tapered surfaces. Okay. So, in construction of this, this particular problem has been taken to figure out that how we are going to model the particular process, whether if the process involves some kind of heat transfer or mass transfer, how we are going to model the process. And so far in our earlier lecture, we have mostly confined ourselves with the Cartesian coordinate. Now, in this particular case, we shall be looking into the cylindrical coordinate. So, this problem is like this, that consider steady pressure flow of Newtonian and incompressible fluid flowing through channel formed by two tapered plates of infinite width. What it means that a pressure flow means the flow is occurring due to some kind of pressure gradient. As we have seen earlier, like Couette flow, in Couette flow the flow occurs not by any pressure gradient but by the relative motion of the two surfaces. So, it is mentioned in this particular problem that it is due to some kind of pressure gradient. And what we mean by infinite width is like this, that if I draw these plates a kind of 3D, it would look like this. So, you can imagine that we have two plates of like this. So, this particular width is taken to be infinite. Okay. So, this is this. So, we have these two plates. So, we have two plates like this, and through which this particular thing is going out. Now, when this fluid is moving, you can see that there could be, because this tapering is there, it may be assumed that there could be some kind of there is a axis here here you can see that the axis over which this particular thing is there. So, these plates have some inclination of alpha over here. Okay. So, this is just giving that the angle of the tapering, and this you can see that the fluid height is changing as it is moving there. So, whatever coordinate system is being used, the origin is taken on this axis. Okay, this should not be confused that we are not taking this as the origin, but we are putting some axis around which as if this particular thing is as if it is rotating. Okay. So with this consideration, we are saying that here we have shown the z axis and r axis. So r is corresponding to the radial distance from this particular axis. Okay, and theta is this direction. Theta is this direction around the axis. Okay, so this is the theta direction. Okay, and this is the r direction, this is the z direction. So in this fashion, we can see that if we want, the question asked is that the fluid is being heated from the outside to maintain its wall temperature at a constant value of TFW. That means as if you are having here, we have a value of TF, that's fluid at the wall. Okay. So similarly on this side also you have TF wall temperature. Okay. So that means this is a Dirichlet kind of condition. So it is assumed that the fluid is at a different temperature from the wall. So there will be some kind of heat transfer from the wall to the fluid. So derive the relevant equations to find the temperature distribution. It will be distribution through the fluid. Now because the fluid is moving, so we know that even if you want to take the temperature distribution, it is that you have to consider the energy balance equation, and in the energy balance equation we have the inertial term that is due to the flow of the fluid. So if we want to find out the temperature distribution, we should also know the velocity profile that will dictate the temperature distribution. So what we shall do now, we shall see that how we are going to make the balance equation. So first we shall go with the coordinate axis that we have chosen, cylindrical coordinate, and here we are assuming that VR, that is the radial velocity is in this direction. Okay, this is the radial velocity direction. So this is VR. So this VR is taken to be a function of r and theta, and V theta and Vz are taken to be 0. That means we are considering a one-dimensional flow. Also we are considering the liquid to be Newtonian and incompressible. That means we are assuming that the density is remaining constant, or also we make one assumptions because nothing is given in the particular problem. So if it is a gas, you may take the viscosity to be a function of the temperature, or for liquid, for some small range of temperature, you may consider the viscosity to be a constant. But these are not very restrictive assumptions. Okay. So let us now go further. So here we first go with the continuity equation, because we always know that mass balance has to be maintained. So we go with the continuity equation. Now you see that in the rest of this particular problem, we shall be sticking to the cylindrical coordinate system. So you see that we have taken this cylindrical coordinate system, the continuity equation, and here we are assuming that there is no variation with respect to theta and the z, so that these two terms are taken to be 0. Okay, and because it is incompressible, so we are taking this to be 0, and this rho is taken out of the differential. So with this we find that we are obtaining this particular equation, and from this we find that it means that r VR is some kind of a constant, and this constant is a function of the theta. Okay. So this f theta signifies this particular constant. This is a function of the theta. That is why we are finding that V r theta is equal to f theta by r. That means the VR is going to decrease with an increase in the velocity, increase in the radius. Okay. Now after writing this particular thing for the, see, these will be generally used later on when we go for the solution of these equations. We will be needing this particular relationship. Now we go for the momentum balance equation. So this is the momentum balance equation for the r direction. This is for the theta direction, and we have another for the z direction. So we shall come to that later. So here we have the r direction. Now again you see that in this we are assuming, as per the problem, we are assuming it to be at steady state. So this particular term will go to 0. Okay, and then we are assuming that it is independent of the theta or it is axisymmetric. So this particular thing goes to 0. Okay, and this is also going to 0 because there is no variation with respect to z. Okay, and then this is also going to 0 in similar fashion. This is also going to 0, and here we have this particular thing. You see that this, in the problem we are saying that the v theta term is 0. That means there is no rotation. Now you can looking at this particular equation, you understand that this is something to do with the centrifugal force that is acting on the fluid. Okay, in that, and you know that centrifugal force always acts radially. Okay, so that is why you find that whenever you are writing the radial momentum balance in the cylindrical coordinate, you always have this v theta square by r term that to take care of the centrifugal force. But in this case, this is absent because as per the question, this v theta component is 0. Okay, so and we are assuming that there is no body force. So this particular thing in the radial direction is taken to be 0. Okay, and so we are left with what? We are left with this particular thing, Vr, dou Vr by dou r, then dou P by dou r, and this mu, this thing. Okay. Now you can see that this dou Vr by dou r, if you go back to this continuity equation, you go to the continuity equation, what you find that dou Vr is something like minus f theta by r square. Okay. So this is dou Vr by dou r, and then you find that f theta by r is nothing but, so this is dou Vr by dou r is nothing but minus Vr by r. So with all this we find that this dou Vr by dou r will give you minus Vr square by r. Okay, and here we have this particular term. So you can put this, you can expand this term, and you will get this particular type of equation. Now you see that what is happening, that in your this pressure drop is due to the viscous force. Okay, and next we come to the theta direction. Now even though there is no theta component of the velocity, but you will find that in the theta direction there could be here in this case you see that this is going to 0 here, this is going to 0 here, this particular thing going to 0 here. So all these things will go to 0, and here you find another term is coming which I am explaining. So you will find that this particular term is signifying the Coriolis force. Now Coriolis force is something which happens whenever there are two motions combined. One is radial motion and one is the theta direction motion. Means, so when you go to a merry-go-round, suppose you are in a merry-go-round and you are walking on the merry-go-round, you will find that you will be experiencing a force that will try to not just throw you away, but also kind of either take you along the circumference direction. That means if a liquid is flowing over a rotating surface radially, then the liquid will find that as if it is getting spread over the particular surface. Okay, and this particular force is called the Coriolis force. So this is the centrifugal force, and this is the Coriolis force. Okay. So, these two forces come into picture whenever you are having a motion in the theta direction. Okay. And of course, in this case all these v theta components are 0. So, there will not be any kind of Coriolis force, and we see that only thing what is remaining is this particular term. Okay. And if we take that Vr is also constant with respect to theta, then this will also go to 0, so that there will not be any kind of pressure drop along the theta direction. Okay. But in our problem we are taking that Vr is a function of both r and theta. So, this will be a non-zero value. So, this will not be equal to 0. Okay. That is why we have to, even though v theta is 0, but due to this particular component we find that there will be a pressure drop along the theta direction. Now, let us come to the other direction, that is the Vz term. Now, in this case Vz, you see that there is no term in this which is non-zero, because see, if you look at Vz component is anyway 0, so all these things will be 0, and here you will also find that there is no Vr term. Okay. So, there is no Vr term, so naturally everything is going to be 0, and there is no, we are also considering that there is no body force, even though in the z direction there could be a hydrostatic gradient due to this gravity, but looking at the particular problem we may say that the height of the liquid confined within these two plates may not be substantial to exert enough hydrostatic gradient. Okay. With that logic we are saying that dou p by dou z equal to 0, but again you mind it that this hydrostatic pressure drop will depend on the height of the fluid. So, if you have substantial height of the fluid, then you can consider that particular thing, and then it will be something like this. It will be minus dou p by dou z equal to rho into g. Okay. And from this you can get p equal to rho g h. So, if this h is very, very small, then you can neglect the effect of the hydrostatic head. Okay. So, this is all about the momentum balance equation, and now you can see from these equations you can find the velocity. Now, this velocity will be required to solve for the temperature distribution, and here you have it that you now write the energy balance equation. So, on this left hand side you have the inertial terms, and you see that again v theta is 0, Vz is 0, okay, this steady state. So, there is this dou t by dou t will be also 0. Then we are assuming that there is no gradient with respect to theta and z, so these two terms are also 0, and in this case we are neglecting any kind of viscous dissipation. So, we are taking this particular term to be also 0, and in also there are no reactions in this particular system. So, there is no other source term associated with this particular case. So, with these assumptions we find that the dou t by dou r is coming like this. That means the gradient of temperature along the radial direction will be dictated by this, and here you see that this alpha is the thermal diffusivity, that is the K by rho Cp. Okay. So, this is the equation which we wanted to derive to find out the temperature distribution within the fluid. So, you see that from this particular problem, even though our main concern was to get the temperature distribution and which was to be obtained from the energy balance equation, however, due to the involvement of the velocities or the inertial forces in the energy balance equation, we need to go to the momentum balance and also the continuity equation. So, that is how you find that the whole problem becomes a bigger problem, even though the concern is only for the temperature. So, if you can assume these velocities to be constant, there is no gradient, then we need not solve the momentum balance, we can just go directly to the energy balance equation. So, I will be stopping here, and as you can see that as for the given problem, the temperature, to solve this problem we need two temperature boundary conditions. So, what we can do that we can take one boundary condition near the inlet and one boundary condition at the outlet, okay, and because we are maintaining the temperature constant at the wall. So, we may say that the whole at any axis we can assume that there is a good amount of mixing along the axis. So, the whole temperature is constant along the the z direction. Okay. So, for this particular problem to solve, you can give two conditions. One you can specify at the inlet, and you can another boundary condition you can specify at the outlet of the particular channel. Okay. So, that is how you can solve this problem. Next, we go to a problem which is concerning the mass transfer. In this particular problem, you see that we have to consider the evaporation of a volatile component liquid A into a pure B in a tube of infinite length. The liquid level is always maintained at z equal to 0. It is something like this, that suppose this evaporation problem you find many a times, like from the ponds, from the river, from the ocean, you get the liquid is evaporating, and in that case we say that this infinite means that if I consider the atmospheric to be of a infinite length, okay, so what happens that this particular liquid goes into the atmosphere, and nearby the interface there will be some gradient, but as we move away from the surface of the liquid, we find that this gradient, this concentration of the particular species which is evaporating will also come to constant. Or for example, you find that when we are trying to dry some kind of material or clothes, what we do that we find that in the we put some fan to make it dry faster. And why we do that? Because when this particular component is evaporating from the wet surface, it forms a mass transfer boundary layer near the surface, okay, and that creates a resistance to the mass transfer or evaporation. Now, the more the humidity in the atmosphere, we find that it takes longer time because this particular boundary layer thickens. Now, why we run the fan is that by running the fan, we are trying to destroy the formation of the boundary layer over the wet surface, so that we can maintain the large enough gradient for the solute to, or the in this case water, to go from the wet substance into the atmosphere. So, this is the kind of problem we consider, and we see those kind of how to model those kind of problems. So, here we have to develop appropriate balance equation to determine the concentration profile of the evaporating component A, and the assumptions taken are that temperature, pressure remain the constant, and vapor of A and B from the ideal mixture. It is not a very restrictive assumption, but by putting ideal mixture we are just trying to simplify our analysis. Then diffusion coefficient is taken to be constant, species B is insoluble in A. It is something like this, that suppose when water is evaporating into the atmosphere, we assume that the components in the air, that is, if majority of them is nitrogen and oxygen, we assume that this nitrogen and oxygen are not coming back into the water. So, from practical purposes, we assume that the air is insoluble in water. Okay? So, that is the meaning of this particular assumption. The overall concentration of the species remains constant. Now, let us go. Now, if you look at the continuity equation, you find that we are assuming only the movement in the z direction, that is in the axial direction. So, we are for the timing we are not considering the spread of the solute or in the theta direction. So, we are having that dou Vz by dou z equal to 0. Okay? and here we are, this Vz is the z component of the molar average velocity, because molar average, because we have both A and B components together. Okay, because even though A is going into the thing, but once it go into the B phase, then we find that both A and B combine, and the velocity of the A will be dictated also by the presence of the B, and these things are covered in more detail in the mass transfer analysis. So for the timing, I am not going into those details. So from this equation we find that Vz star can be written in this particular fashion. Okay, and then we find that this Vj star is the velocity Vz at z equal to 0. Okay, and then we go for the species balance equation. So this is the overall mass balance, the species balance equation, and the species balance, again we take the inertial term, that is this inertial term, and this is due to the diffusion term, and there is no reaction between A and B. So that is why we are writing that dou x by dou t equal to this, and you understand that dou x by dou t, here it is because we are assumed that the overall concentration remains the same. So this it is essentially dou Ca by dou t, but then this Ca is taken as the overall concentration into Xa. Okay, so this is taken, this constant, so this is going out of the differential, and we are having only Xa over here and Xa over here. So this is the basis of writing in terms of the mole fraction. And this nabla Xa, as you know, this nabla is nothing but the gradient of Xa. So nabla is, you know, that this is, say in the Cartesian coordinate, it is dou x, then okay. So this is nabla. So this nabla into Xa gives the gradient of Xa. Okay, and this one is the delta square nabla square meant it will be the scalar. So this is the nabla square is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Please understand, we are not writing in ijk over here because this is a scalar. Okay, so this is how we are able to set up the material balance equation for this condition. So here we see that when I am writing those x, that should not be confused with the Xa that is being used to represent the mole fraction. Okay, that you should be careful about. So this Xa is the mole fraction. This is the mole fraction. Okay, and when we are writing only x, that is the signifying the coordinate direction. Okay, this should not be confused. Sometimes this mole fraction is also represented in terms of Ya. Okay, so generally what happens that when we talk of the gaseous phase, we put in terms of Y, and when we talk about a liquid phase, we put in terms of X. So these are some conventions. Okay. So now let us see that this particular problem would be completely defined only when we have the initial condition and the boundary condition, because here we find that this particular equation has an unsteady state term, and also it has some differential with respect to the coordinate direction. So let us now see how we shall be specifying the initial condition and boundary conditions. So here we have the initial condition that as if at in the phase B there is no Xa to start with. So we are putting Xa equal to 0, okay, for all Z. And understand this Z is being taken from the interface between A and B. Okay, and this Z is moving inside the B. Okay, from the interface of A and B, it is moving inside the B. Okay, so that is the meaning of that all Z. And then for the boundary condition, we are assuming some kind of interfacial concentration of A, at the boundary, that is given by x is 0, and that is the meaning of z equal to 0, and for all t, and for z equal to infinity, that means at a large distance from the interface, we are assuming that there is no xa, that means it is going to 0. Okay, so that means if we can without any solving, we can say that if we plot, suppose we are plotting, so this is z equal to 0 and this is z is going to this is z direction, okay, this is straight line. So if we are seeing the concentration, okay, we can check that this is as if going to, it is some xa 0 value here, okay, and it is going to a 0 value. This is, now you see that in this particular expression, do not confuse this xa with the coordinate direction. This xa with this subscript signifies it is the mole fraction of component A. And in the Nabla operator also we wrote the x, but in that case the x is the direction of the coordinate. And many times in the literature you will find that we are using either x or y to represent the mole fractions, but generally these x and y will be accompanied by a subscript. So that will make it different from the coordinate axis. Now, this problem can be solved only when we have the appropriate initial and boundary conditions, and because it is a unsteady state situation, so we need some initial condition, and in this particular thing we find that we have the second degree in the derivative, and because it is one dimensional in the z direction, so we need two boundary conditions in the z direction. Now, in this case you see the z is taken to be the interface between A and B, and the positive z direction is taken to be going inside the B phase from the interface. Okay. So, with these considerations, let us go to see how we are going to specify the initial condition and boundary conditions. So, initially at t equal to 0, we say that there is no A present in the B phase or in the gaseous phase. So, with that consideration, we take that xa is equal to 0 for all z. And for the boundary conditions, we say that at the interface, that is at z equal to 0, we have xa equal to xa naught, some specified value, okay, and for all t more than 0. And then another condition we take that at z equal to infinity, that is much away from the interface, the amount of the A is taken to be 0, that means nothing is present. So, this can be all these things can be represented like this, that if I consider that this is the interface, okay, this is the z equal to 0, and from here I am counting, this is the B and this is A is coming from here, okay, and this is the z direction, okay. So, here we are taking xa, at this position we are taking xa equal to some xa naught, okay, xa naught. Now, here understand this, that when I putting xa naught, it means that this A is not a pure component, it is in a mixture, okay, and we are assuming that other than A, no other component in the liquid mixture are volatile. So, only A is the only volatile component which is going into the B, okay. Now, suppose this is, with this I also take as the, suppose this is I take as the coordinate axis for Ca, or xa, okay, Ca or xa suppose. So, if we make the profile of the xa, so we will find that from this, suppose this is z equal to 0, so we find that profile will look something like this, okay. So, it is Ca is 0 here, so and this is the value, we call it xa naught, okay. So, this is how, and this profile will be a function of time, okay, this was a function of time. You will find that at different times you will have different profiles like this, okay. So, this is the way we visualize that, this is the way this profile of the A component will be developing with time. So, this is a qualitative understanding of the concentration distribution of a component which is evaporating in another component. So, with this we can complete the formulation of this particular problem to get the concentration distribution of an evaporating component. These are the references which you can consult for more detail of these particular processes. Thank you.